Today I have something that will challenge your understanding of the workings of the universe. Dr. Robert Sungenis, a prolific author, is a pioneer in the research of cosmology. He has co-authored a 3-volume work entitled Galileo Was Wrong, the Church Was Right.
Basically the same thing. It's either smooth or not smooth. Okay, that's basically what it all boils down to. We have a smooth universe or we have a patchy universe. Okay? The Big Bang wanted a smooth universe, but they began to see a patchy universe up there in the sky. So about 10 years later, they sent up a satellite probe called the COBE probe. The was oriented around its axis. Okay? So, and they were in consternation again. How could this possibly be? This goes against the Big Bang Theory. It puts the Earth in the center of the universe. As a matter of fact, that same professor I talked about before, Lawrence Krauss, wrote a paper in 2006. It was about a totally different topic. He was talking about the quantum field. And then at the end of the paper, and it was just a casual paper, but still, it's coming from him. At the end of the paper, in the last 2 paragraphs, he talks about the cosmic microwave background radiation and what they discovered from this 2001 Wilkinson probe. And he says, well, that means we're in the center of the universe. Now this is a guy who's a heliocentrist. He's an atheistic, a modern Big Bang cosmology professor. And he says, yeah, it looks like this cosmic microwave background is putting the Earth in the center of the universe, or our whole physics is wrong and we need to revamp it. So he leaves himself that out. That, we could be wrong about everything. So he needs to start from square one, so to speak. And anyway, and this puts another wrench into the works of that, because now you have to explain where these anisotropies come from. Where does this inhomogeneity come from? The Copernican principle. That's the lens, if you want to call it, that they see the data through. As a matter of fact, we were talking about Lorentz and Einstein, and when they were trying to answer the Michelson-Morley experiment. Well, they came up with every conceivable answer to explain the Michelson-Morley experiment, except the very one that's the most obvious, and that's that the Earth is standing still. Because they were so influenced by the engine of modern science at that time that had accepted as dogma Copernicus' principle that the Earth was moving, that they were so blinded by it that they couldn't see anything else. And it's interesting when Ronald Clark wrote the biography of Einstein. He's one of the major biographers of Einstein. He says he was the one that admitted that the Michelson-Morley experiment, in several places in his book, it's 800 pages long, but in several places he admits, he says, after the Michelson-Morley experiment, we had 3 basic choices. And one was special relativity. The other was that the Earth was moving with the ether. And the other was that the Earth was standing still in space. And then he closes that sentence and he says, but that was unthinkable. That was unthinkable. In other words, we know that that's a possible solution scientifically, but we just can't go there. We just can't go there because we know the ramifications of it.
We can't say anything or we can't say anything that would give any kind of credibility to sacred scripture, right, Doctor?
Yeah, because the whole agenda since the time of Darwin in the late 1800s has been to put the Bible in a box, basically, and now use empirical science to prove that the Bible has been wrong all along. And if Copernicus showed us that the Bible was wrong about the Earth being still in space, being fixed, well, then what else is the Bible wrong about? Well, hey, you know what? The Bible can be wrong about
morality. Anything.
Yeah. Wrong about morality. As a matter of fact, there's a whole hermeneutic in a special place in the universe. And that means that if all this scientific evidence we find is true, and I have no way to explain it away, I have to, as a scientist, submit to it. And if I submit to the scientific evidence, I have to submit to the ramifications, philosophical and metaphysical ramifications
of that scientific evidence, which puts me as a creature created by the great creator, and that means I'm responsible to him.
And this agenda that is out there, it seems to be driven by an elite that wants to keep this information from forming minds, young minds in universities and colleges all around the world. And in that sense, is modern science corrupt?
Yeah, modern science in many ways is corrupt. I have a whole chapter on that in my book. And I show not only in the field of cosmology, but also cosmogony, medicine, anthropology, paleontology, psychology, sociology. I mean, all these disciplines are controlled by money, by people with cultural agendas, by atheism, and you can go down the road and see how all of them, and because of all these pressures that these scientists are under to conform to the status quo, and the status quo basically is atheism, well, they're going to interpret the data accordingly. And that's why my big thing here is the Copernican principle. That's the lens, if you want to call it, that they see the data through. So what does modern science do with that? And it just so happened that there was another scientist named George Fitzgerald who had come up with the same idea that Lorentz had come up with right around this time. And to them, said, okay, well, let's go back to the laboratory. And James Clerk Maxwell had suggested this experiment to Albert Michelson. James Clerk Maxwell was a very famous physicist who gave us his electromagnetic equations. He had suggested that they do experiments on light in the laboratory as opposed to on the stars. So Michelson came up with this thing called an interferometer. And what an interferometer does is it takes two light beams and it sends them on a path. And then on the path back to the receiver, the light beams will either coincide in their wavelength or be disrupted in their wavelength. That is, the crest of one will meet the crest of the other, or the crest of one will meet the trail of the other. And if the crest meets the trail of the other, that means they're out of phase, they're out of sync. And these will cause fringe, what they call fringe shifts, fringe, F-R-I-N-G-E, shifts in a receiver that receives both these light waves coming back. And depending on the displacement of these fringe shifts, you can tell how much the waves have been displaced from one another. That is, you can tell whether wave A came back faster than wave B. All right? Now, they shouldn't be coming back faster. A and B should both be coming back fast, that's at the same speed, because light travels the same. You know, whatever way you shoot a light beam, it travels the same speed in whatever direction you point it. At least so they thought. Okay. The idea behind the interferometer is this: if we shoot a light beam, let's call it light beam A, from east to west, okay, east to west, that's the direction that the Earth is supposedly revolving around the sun. Okay, it's moving counterclockwise around the sun, and that's from west to east. Okay, so if we shoot a light beam from east to west in the opposite direction that the Earth is supposedly revolving around the sun, then that light beam should go slower than a light beam that is shot from, let's say, the equator up to the North Pole. All right. The reason for that is if there's a resistance, let's just say the Earth was revolving around the sun and yet space was filled with air. Well, what would we expect? Well, we would expect that if we shot a light beam through that air, it's going to go slower than if we shot the light beam from the equator to the North Pole, because the light from the equator to the North Pole is not having the same resistance as the light shot from east to west. Okay? Does that make sense?
It does, because one, it has no, it's not fighting against anything. It's just going in a straight line. The other is having to contend with going around the sun in the opposite direction. Is that what you're trying to say?
That's right. Yeah. It's just like if you were in a pool of water, and there was the water. What do they call those pools where the water automatically is creating a wave for you? You can go surf on them and all.
A wave making machine.
Yeah. So now, if you're in the pool, well, there's a certain resistance now. That water is going by you, so there's a certain resistance. And if you shot a light beam in that water that was moving towards you, it would go slower than if that water was going the opposite direction, okay? Because there's a resistance there. As a matter of fact, that's what all these other experiments in the 1800s found. Martinez Hooke and a few others found that light was slower in water that was going the opposite direction. So if space is filled with ether, which is a substance, well, that means that a light beam shot from east to west in opposite the presumed revolution of the Earth, well, that light beam would go a little slower than one shot from the equator to the North Pole. So this is exactly what Michelson's experiment did. He did the first one in 1881, and he shot. What he had is he had a table, and the light beams would go back and forth, and then he shot perpendicular light beams across those, and so you had basically light beams going at a 90-degree angle. And he found that when he rotated the table to try to make the light beams coincide with the revolution of the Earth, he found there was no difference in the light beams traveling east to west as opposed to those going from north to south, or south to north. And this was disconcerting because the whole theory was that the ether would form some kind of resistance against the east-west light beam, enough where they could show that the Earth was moving at 30 kilometers per second around the sun. What they got was probably about 1/10 of 30 kilometers per second, let's say about 3 kilometers per second, okay? And so he hired, or he consulted, Michelson consulted with Heinrich Lorentz, who was another famous physicist at that time. And he said, what's going wrong here? And so Lorentz said, well, maybe one of you you have a mathematical miscalculation in one of your equations here, and that's why the figure came out to be, 1/10 of what we expected. And so Michelson said, okay, all right, maybe you're right. So he prepared to do the experiment again in 1887, and he got funding from the National Academy of Sciences in the United States, and also from Alexander Graham Bell.
And this was the Michelson-Morley experiment?
Yeah, this is the second one now. He took on a partner now, Edward Morley, and did the second interferometer experiment in 1887, 6 years after the first one. And basically it was to find out whether the first experiment was valid. Is this result that was totally unexpected in 1881 going to stand up? Okay, so what you do the experiment again. So they did the experiment again, and now they made it even more sophisticated. It was going to be able to measure these light beams a lot more accurately than the 1881 version. And so they did the experiment. They did it over 6 days. They had 36 trials, and it came out to be almost exactly the same result as occurred in 1881. And that is, they expected fringe shifts that were on the order of 30 kilometers per second of the Earth going around the sun, and what they got was, say, between, say, 3 and 8 kilometers per second. All right, heliocentric side. But then you had a lot of people on the geocentric side that you don't hear talking from the sun, then it's going to be farther away from the star at certain times and nearer to that star. Have to be moving with them until you have this point of matter that there's no return, so to speak, in a 10 to the minus 30 Fresnel's explanation. If the Earth is moving around the sun, and it's a pretty good clip, 66,000 miles per hour that it would have to be moving to complete that revolution in 1 year. So that's pretty fast. That's 19.5 miles per second. Well, if that's the case, then the light coming from a star, if it hits the water telescope, we would have to tilt the telescope, that water telescope, to the lower end of that star in order to catch the light rays to be the same as if they were going through the air telescope. The reason, moving the light in such a way where it would not require a rago to refocus his telescope. Now then there was another experiment done that was similar to Arago's, and this was done by a guy named George Bedell Airy, A-I-R-Y, and he was a very famous astronomer royal from England.
I thought his experiment was one of the most persuasive, in my opinion. But please continue.
Yeah, it was very persuasive, and the reason he did that was he was going to determine whether Fresnel's explanation of Arago's experiment was valid. And so what Airy did was, instead of one telescope, he got 2 telescopes side by side, and one was filled with air, of course, and the other was filled with water. Now, the basis for this experiment was this. If the Earth is moving around the sun, and it's a pretty good clip, 66,000 miles per hour that it would have to be moving to complete that revolution in 1 year. So that's pretty fast. That's 19.5 miles per second. Well, if that's the case, then the light coming from a star, if it hits the water telescope, we would have to tilt the telescope, that water telescope, to the lower end of that star in order to catch the light rays to be the same as if they were going through the air telescope. And the reason for that is this. Light goes slower in water than it does the air. So if that light, because of the Earth's movement, in other words, if the telescope needs to be adjusted so that the telescope gets all the light of the star, even though the Earth is moving very rapidly around the sun, well, that means we're going to have to tilt that telescope just a little bit more toward the lower end of that star to get all the light that the star has to offer. And you can compare this, for example, to when you're walking in the rain with an umbrella. Let's say that you're standing still, first of all, in the rain with an umbrella. The rain is coming straight down on you, and so you don't have to move your umbrella. You just hold it straight up and down, and you don't get wet. But let's say you started running with your umbrella. Well, what's going to happen then is some of that rain, it's still coming down straight, but as you're moving, you're actually moving into the rain, and it looks like the rain is going on a diagonal, and it's going to hit the pants or the shoes of your garments, unless you tilt the umbrella toward the direction that you're running in order to stop that rain from hitting your shoes. Okay? Well, that's the same principle here with Airy. He said, in order to catch that light, I have to tilt the telescope a little bit more, the water telescope that is, and that will prove that the Earth is revolving around the sun. If I have to tilt this water telescope a little bit more toward the star. Lo and behold, what did he find? He found that he did not have to tilt that water telescope toward the star as compared to the airfield telescope. They both had the same refraction. That is, the light was coming in from that star as if that star was right overhead, and it was coming straight in, and it went to the eyepiece of both telescopes without hitting the side of the water telescope. And that's what he expected. He expected the light beam of the star to hit the side of that water telescope, and that would prove that the Earth was revolving around the sun. But it didn't. It went right to the eyepiece of that telescope. And that means that, hey, the Earth is not moving. Because if it was moving, he would have had to tilt that telescope.
Yeah.